To understand the concept, try to understand this model. Here I have taken the circular coil, model of the circular coil with the radius capital R. Here it is the center of the circular coil O. Let current I is flowing in an anti-clockwise direction. So we know that already the current carrying conductor can produce a magnetic field around it. From the center of the circular coil at the distance Z, we have the point P. Now we are going to find the magnetic field at the point P, which is given by this circular coil. For that, we are going to take the two line elements at C and at point D. So using the Biot-Savart law, we can find the magnetic field given by these two line elements, and that value want to be integrated. Then we can find the net magnetic field given by this circular coil at point P. Here the distance between the line element at C and the point P is R. Likewise, the distance between the line element at D and the point P is also same R. That means line elements are at the same distance from R. Hi everyone. Today we are going to discuss about magnetic field produced along the axis of the current carrying circular coil. For that, let us consider a current carrying circular loop of radius R, and let I be the current flowing through the wire in the anti-clockwise direction. The magnetic field at a point P on the axis of circular coil at the distance Z from the center of the coil O can be calculated by taking two diametrically opposite line elements of the coil, each of length dl, at points C and D. Now, by using the Biot-Savart law, we can find the magnetic field at the point P due to these two line elements, that is dP. By integrating that value, we can find the magnetic field produced by this circular coil. As per Biot-Savart law, let R vector be the vector joining the current element ideal at C and the point P. Now we are going to use the Biot-Savart law to find the magnetic field at a point P due to the current element at C. So dP, that is equal to mu naught by 4 pi ideal cross R cap divided by R square. So let it be first equation. So it is a vector notation of the Biot-Savart law. Here ideal cross R cap is there, so we can use the cross product. So ideal cross R cap, that is equal to modulus of ideal into modulus of R cap and sin theta. So in a vector product we have to write sin theta. What is the value of modulus of R cap? That is nothing but a 1. So no need to write that. So modulus of ideal sin theta can be substituted in a first equation. Here I have applied the new value in equation 1, which we have obtained from the cross product. Now we have to find the value of angle theta. In this case, what is the angle theta? Value of angle theta is 90 degree. So in the Biot-Savart law itself, we have learned the angle between the R vector and the current element is always 90 degree. Both are perpendicular to each other. So angle theta is 90 degree. So sin 90, that is equal to 1. So that can be substituted in a equation. The magnitude of the magnetic field at point P due to the current element at C we have found so far. So that will be same for the current element D also, because both the current elements CD are placed at the same distance from the point P. To understand the concept clearly, I have taken the model of the circular coil. Here it is a current element at C. Here it is a current element at D. Imagine steady current I is flowing through the circular coil in an anti-clockwise direction. At point C, the current flow in this direction. To find the direction of the magnetic field at C, we have to use the Maxwell's right-hand corkscrew rule. For that, imaginary screw want to be moved in the direction of current. For that, we have to rotate the screwdriver in an anti-clockwise direction. So the magnetic field produced in the C also has the anti-clockwise direction. So due to the current element at C, the direction of the magnetic field acts in this direction. So it is in an anti-clockwise direction. Now we are going to find the direction of the magnetic field due to the current element at D. Remember, the current element at C and current element at D both are diametrically opposite to each other. They both are creating the magnetic fields with the same magnitude, but direction is different. Because the direction of current at D is different from the C. Here it shows the direction of the current, that is anti-clockwise direction. So you have to rotate the screwdriver in a clockwise direction, then only an imaginary screw can enter into D in the same direction of the current. So the magnetic field due to D has the clockwise direction. As we have discussed, the magnetic field at the point P due to the current element at D act in a clockwise direction. So it will act along PS. So like this it acts. The magnetic field given by the current element at C act along PR, anti-clockwise direction. The current element at D produce the magnetic field in a clockwise direction, it act along PS. To find the direction, let us take the frame of reference which is given in your book. So keep your fingers like this. Forefinger shows the Z axis, middle finger shows the Y axis, and thumb shows the X axis. The magnetic field dB due to each current element is resolved into two components. dP cos phi, they are the horizontal component, it act along Y direction, and dP sin phi is a vertical component, act along Z direction. The horizontal components cancel out because they are in opposite direction. The vertical components dP sin phi alone contribute to the net magnetic field B at the point P. Now to find the total magnetic field given by this circular coil at the point P, we have to integrate the magnetic field given by the current element. So the net magnetic field B vector, that is equal to integration of dP, that is equal to integration of the vertical component. So here vertical component only gives the magnetic field. So vertical component acts upwards, that means it acts along Z axis. So that's why we have taken the orthogonal vector k cap. Now we can apply the value of dB from the first equation. So from the first equation we can substitute the value of dB. Here I have substituted the value. So in this expression, constant values can be taken out of the integration. So what are the constant values are there? So now constant values are taken out. So we are going to integrate dl by r square sin phi k cap. Now we can take the triangle OCP. So in the triangle OCP, I am going to find the sin phi value. So what is the formula for sin theta? Opposite side by hypotenuse. What is the opposite to the angle phi? R, capital R. So capital R divided by hypotenuse value, that is nothing but a small r. So capital R by small r, that is a sin phi value. We can find the value of the hypotenuse small r using the Pythagoras theorem. Hypotenuse square, that is r square, that is equal to sum of the square of the other two sides, that is nothing but a capital R square plus Z square. From there you can find the value of As small r, that is equal to r square plus z square power 1 by 2. Instead of square root, I have written 1 by 2. That value can be substituted in the expression. So here I have substituted the small r value at the denominator. So here we have two values. So one is sin phi value and r square value. Both the values can be substituted in the expression of the magnetic field. Here I have substituted the value of the r square and sin phi value in the expression. So at the denominator we have r square plus z square, r square plus z square power 1 by 2. So base is same, so we can add the powers. So 1 plus 1 by 2, that is nothing but a 3 by 2. So here at the denominator r square plus z square power 3 by 2 is there. So that can be taken outside. Here once again I have taken the constant values outside. I am going to integrate only the dl. dl is nothing but a length of the line element. If you are going to integrate the length of the line element, so then you can get the length of the circular coil, that is nothing but a circumference of the circle, that is 2 pi r. Instead of integration of dl, I have written the 2 pi r, that is nothing but a circumference of the coil. So what are the things can be cancelled? Pi can be cancelled, 2, 4 can be cancelled. At the numerator we have r into r. So r into r square will be there. So I have written the new expression. It is the expression for the magnetic field which is given by the circular coil which has the one turn. Suppose this coil has the n number of turns, this expression can be multiplied with number of turns. So here it is an expression for the magnetic field given by the circular coil having the number of turns capital N. So as number of turns increases, magnetic field is also increases. Here O is the center of the circular coil. Imagine if point P lies on the O itself, then what is the value of Z? That is equal to 0. So in this case we can neglect the Z value in this expression, so it can be substituted as 0. So what is the new expression? Z is 0. So new expression P vector that is equal to mu naught Ni by 2 r square, the denominator r square power 3 by 2. So 2 can be cancelled. Remember square 2 is there. So 3 by 2. So 2 can be cancelled. So what is the new expression? R cube. Here r, the denominator r cube is there. So r square, r cube can be cancelled. At the denominator what is the new value? R will be there. Here the magnetic field B vector that is equal to mu naught Ni by 2r. So it is a expression for magnetic field at the center of the circular coil which carrying the current.